Okay. Good morning, everyone. So we're very happy to have this Homotopy Theory Day at NYU. We have a very interesting set of talks today, and we're going to start this morning with Sadok Kallel from American University of Sharjah, who's going to tell us about Homotopy type of graph configuration spaces. Sadok,
all right, thank you so much. Okay, I hope you can all hear. Well, thank you so much again for the invitation and for being here at NYU. Again, it's always a pleasure to be with you. So it's a homotopy type day, and I thought I could talk about homotopy type of graph configuration spaces. Okay, so this is joint work with Moaz Bouzouita and University of Tunis. Okay, so what are those? I'm trying to do this. Sorry. Okay, so if you take an abstract graph given by vertices and edges, these are not configuration spaces on the graph. This is a totally different construction. Okay, so if you take an abstract graph given by vertices and edges, then you will you construct this space for any x, a nice space, nice enough space. You can construct this configuration space. So it's tuples of points, as many points as we have vertices in the graph, and you say I is not equal to j if ij is an edge. So, of course, they're labeled, so because these are ordered guys, and different labelings produce homomorphic spaces, so you can, and if the graph is not connected, you get this kind of splitting. So it's really without loss of generality, all graphs are connected. There'll be simple, no loops, nice graphs. Right. And then you get this nice space for any x. So it's like a functorial construction. So if you have a complete graph, right, where any two vertices are joined by an edge, you get the usual configuration space of pairwise disjoint point, which distinct point, which people stand a lot. For example, if I look at the line graph on n nodes, one all the way to n, then this is this subspace for any x. So there are n, so tuples, all tuples of n points in x, ordered ones, and xi is not equal to the next xi plus 1 all the way to. Okay. So in this case, all right, so what I'm interested in, obviously, the whole purpose of this talk is to give you hopefully homotopy type works. And so here's an example where you can work it out by hand. When you have a line graph, then the configuration space is homeomorphic. Actually, it's homeomorphic to this product. So it's a homeomorphic to product of spheres. And the spheres are going to show up all over the place. Right? So you have this nice map because x1 goes to x1, but this is not 0, this is not 0 because everyone to the next are distinct. And you can go back. So for the line graph, we know what not only the homotopy type, but it's homomorphic to this thing. Okay, so this gives you a nice functorial construction, contravariant, you can check. And in fact, just to motivate this whole study, I knew about these spaces a long time ago, and telling you as we go, some of the people who worked on this, not that many, but we really needed them for doing some data analysis. So they're just not something unusual. Great. So this work, another work with Mr. Farhat at the US and Mr. Zlotko, where we're trying to use data which come in the form of graphs and try to use some construction on those to classify the data. It is a big topic now. Okay, so I'm going to start a little slow and try to get to the main theorem of the talk. All right, so if you have a graph, you have something called the chromatic polynomial, right? And the chromatic polynomial is a polynomial, right? And the degree of the polynomial is actually the number of something here. Oh, this should be a lambda. Is the number of vertices, right? And it's the number of ways you can color the number of ways you can color the graph with T colors. So, for example, if you take this guy here, you want to color this. So we have T colors, right? So you will put T colors here. But what does it mean to color a graph? It means that the color of adjacent vertices are not the same. That's the way you color a graph. So here you can only put T minus 1 colors because we already picked one. Right. So you get the number of colors is T minus 1, and that's the chromatic polynomial, right? So if you have the complete graph, you put T colors here, you put T minus 1 colors here. But here you have to put T minus 2. So you get a form factorial like this, which will come in the talk. So this I label like that for this graph, and for this graph it's K3. It's this T minus 1, T minus 2. So you have a polynomial, right? So what's important and interesting, and it's very old stuff, are the coefficients of this. Okay, before I get to there, so I'm going to use the very characteristic with compact support of the space, and there's this really nice result. Oh, sorry. Okay, well, I'm involved, so I should not be saying that, but like surprising little. That's a aesthetically beautiful result, which says this. It says like if you take the other characteristic with compact support of your space X. Okay. So what is that? So I'll tell you in a second. And so you put that as your variable. You feed it into this polynomial there, right? Then what you are going to get is exactly the other characteristic with compact support of the configuration space. So you see the configuration space, the graph. This is called the graph configuration space. This other characteristic with compact support is exactly the polynomial, the chromatic evaluated at. So this was proven a couple, 3 years ago, and the referee pointed out that a baby form of it is here. So the thing is, so just so I see is, of course, the other characteristic of the homology, cohomology is compact support. But if your space is nice, okay, so it has a nice one-point compactification, so you can think of this as something like that, as something like that. So the cohomology is compact support with field coefficient would be the cohomology of the one-point compactification modulo that point and thing. Okay. Although there are various definitions of the cohomology of compact support. So that was the starting point of this whole this inequality. So you get, interestingly, of course, you get the topological characteristic from this. Right. Really is the starting point of this whole thing. Okay, so this meaning I'll get back to it. So here's interestingly how you would prove something like this really quickly so you can see it. So for example, if I take this graph, which is the T graph or the Y graph, how about the Y graph, right? So look how things will work. It's really nice. So different colors are given by different shapes. So this is the way you will color a Y graph with 3 colors. Right? So you have one color here, and these two, because they're not related by niche, they're fine. Right? They can be the same. These can be the same, but this has to be different. Right? So look what you do. To every coloring, that was the idea. To every coloring, you associate a stratum. You stratify your space. You decompose your space into pieces. Okay. Each piece corresponds to a color, right? So, for example, color. So this is label 1, 2, 3, 4. So this would be X1, for example, for the middle one. So that's Y, X, Z, Z. Y and X are different. So these are all tuples of points where Y is not equal to X, not equal to Z. So this is a stratum, this is a stratum, and the univalve strata give you the configuration space. So at the end of the day, you get something like this.
Sorry, Sadok, may I ask, what is T here? Is T,
Where's T?
do you say configuration?
Oh, yeah.
What T?
This is the T graph or the Y graph. Right?
So this was in a subscript before, or what is it?
No, you want to watch? Yeah.
Okay,
Yeah,
so that's-
T button. Thank you. Right. This was old notation. Right. So
Oh,
this
it's the T graph, I see.
and this is the T graph, the configuration of the T graph. So I drew it as a T and then I drew it as a Y. So maybe I should put this configuration of the Y graph. And the configuration of the Y graph consists of what? Consists of tuples of point x1, x2, x3, x4, where x1 is not equal to x2, x1 is not equal to x3, and x1 is not equal to x4. Because they are related by edges, but x2 could be equal to x3, x2 could be equal to x4, x3 could be equal to x4. All right? And then you stratify the space, you cut it into pieces. And now the beautiful thing is that the Euler characteristic with compact support is additive over the strata, as long as the strata are locally closed, which is the case. This is the main property of it, and it's amazing property. So that's why sometimes they call it the combinatorial Euler characteristic. Okay, so that was the proof of that term. Okay, now what we're interested in are these coefficients. I'm not going to even maybe explain what this is in this case, but Whitney rewrote this. Whitney in the 50s rewrote this chromatic polynomial as sum of coefficients, positive coefficients, alternating sign. So as you know, the chromatic polynomial is alternating in sign, and then the log concave or something goes up and down. This was a big theorem proven. So this there is this decomposition where the ANs have an interpretation. Okay, I will not use that interpretation here. I'll just tell you that I will need the term A1, which is the most important to me. It's a linear term. A1 is the coefficient of lambda in that polynomial. All right, am I making sense? I'm building to the theorem. I'm sorry, I will get there. I'll give you homotopy type, but I need numbers. All right, so the number I need is this A1. A1 is that, so let me explain to you what A1 is. I have to reinterpret it, but that A1 is very important because if a tree, for example, if A1 is 1, then the graph is a tree. It's a beautiful theorem, it's an if and only if condition. All right, if gamma is connected, A1 is bigger than 1. You know, so that A1 is important. So what is A1? Okay. A1 is, okay, here's what A1 is. This is what I know. A1 is that an eraser here? Eraser. So you take your graph. So you take your graph, right? So, and you take a source, a unique source, or a unique symbol, a point, vertex, connected graph, right? And you put arrows, right? So it's an orientation, right? And among these orientations, you will avoid having a cycle, right? A cycle, right? So this orientation is not a good orientation. So you're going to orient your graph in all possible ways so that you do not have a cycle. And you will orient it also so that you have a unique source, right? So it's a unique source with no cycle. So this is called an acyclic orientation with a unique source, right? I'll give you an example. So A1 is that number when you count. Right? So this we need.
Sorry, could you say, so source is probably a vertex?
Yeah,
all of
here's
which
an
is,
example.
okay,
Let's take the square, right? So the square has, if you count, we have about 16 or something, different orientation. So I'm taking all these orientation, which are acyclic. So you can go like this, or like this, like this, like this. This is not a cyclic orientation, right? Because you do not form a cycle when you follow the arrows, right? So here, an arrow goes like that, and so, but this guy is your source. All arrows emanate from that point. Okay, so source, 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 source. It's good. Acyclic, 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 acyclic. It's good. All right, but this is a problem. This is a problem because you have two sources. You don't want to have two sources, right? So this is acyclic, one single source. This is acyclic, one single source, acyclic, one single source, acyclic, two sources. I remove this. So when you count the number of acyclic orientation with a single source on the square, the graph which is square, you find 3. But that 3, if you write down the chromatic polynomial, you get exactly 3 with a sign. Okay? That number here, which multiplies lambda, is exactly that A1. It's a beautiful theorem by Stanley. All right? Okay. So what I'm getting to, I'm sorry, maybe it's not really homotopy theory, but it's very good. It's elementary stuff. What I'm building to, I need those numbers because these are going to get into the form. Okay. So that A1 was really nice for us to consider. Now, I need bond partitions. What are bond partitions? So I have to get a little faster. So if you're given a graph, right, sometimes called the connected partition, or so you have a graph, you will look at all the partitions of the vertices, all right, as a set partitions. So you take your vertices 1 through n, and you partition them. The block of the partition correspond to a connected subgraph. That's right. So, for example, here, right? So I take this partition, right? So this is the bond partition would be a special case of the partition complex that people study. So let's see here. So you can take bond partitions of length 3. So what are they? They make 3 blocks. So this is one block. Obviously, it's one edge, one vertex is a connected graph. 2. But then you have to have 3, 4, 5. So you cannot have, for example, 1, 3 and 2, 4. 2, 4, the 2 edges is a subgraph, not connected, but it's not a connected. Yeah, so you get those partitions corresponding to the connected. This is called the connected partition lattice or the bond partition lattice. So to a graph, you are going to associate these partitions. And these partitions, you can put them in the full set. Okay, I'll get to the full set in a second. Am I clear on this? Right. So here's an element of the bond partition. It's right. This is working. All right. So blocks like this, and the length of the whole block is number of blocks is called the length of it. And each block corresponds to a connected sub. Okay. So I said all this, right? And A1 of B is this, right? So I define A1 of B for a block, for a bonded element, sorry, which is consistent of a partition with K blocks. The A1 is the sum of the AIs. So every block corresponds to a connected graph. So I have that A1, the linear term of the chromatic of that guy. Very good. Instead of all on partition, this is the thing. Okay, so start with a finite simple graph, right? And M is the number of vertices, right here. Okay. Then stably after one suspension, that configuration space splits after one suspension into a wedge of spheres of very explicit dimensions. Right. So the homology is torsion free. And everything you think of is nice. And this recovers all results known about configuration spaces, which I'm going to go through. Cyclic configuration spaces studied by Farber, usual configuration spaces, graph configuration, we'll go through this. Anyway, so this is a term. So every element of the bond is going to contribute a wedge summand of spheres of dimension this much, right? This is the dimension of the sphere corresponding to this bond, right, element. Every bond element is made out of blocks in the partition complex, right? And how many of them is it going to contribute? It's going to contribute A1D. Right. So let's do an example. And you get the Poincaré obviously series by taking some spheres. In the literature, so maybe I should say, of course, in the literature, this space has been, the cohomology as a complex, right? So, right, it was computed by books and they recover, but I don't think they knew it at the time. They recover a similar result by from Wheel and Schultz. But these are complexes, so the cohomology is given as a big polynomial algebra, tensor sum exterior algebra divided by some ideal. Nobody knew about what is the Poincaré series or even the stable homotopy. But the cohomology is computed by these two in these two papers. But again, it's as I mentioned, it's given by. Okay, but let's do an example. Just illustrate the theorem on this example. Okay, so I'm going to take the line graph, 1 to 3. All right. So A1 of B for each subgraph is 1 because it's a tree, but you can compute it. So what are the bounds here? Right. So you have, all right, you can take the 3 partition, so the length is 3, 1 to 3, vertex 1, vertex 2, vertex. Each block is a connected subgraph. The vertices. Then 1, 2, because that's the graph 1, 2, and 3. 1 and 2, 3, and 1, 2, 3, the whole thing. I'm going to put this into a post by course. But let's do here. Right? So now you look at the theorem. So for each B, A1, each A1 of these is 1 because they're all trees. So the product of the AIs of each block is 1. So A1 of B is 1 for each. Right? So the S0 is the plus in the stable splitting, so you can forget it. Then here you have the dimension. If you do 3 minus B, the length is 2. So it will be S2. Oh, 1, n minus 1. Oh, I'm doing in R3. It will be S2. So S2 wedges 2 wedges S2. Okay, but that's not a surprise because we have shown that this guy is R3 minus 0 cross R3 minus 0, so S2 cross S2. So when you suspend S2 cross S2, you get S2 wedges 2 wedges. So it's not a surprise at all, right? So it's that for the line graph, that's what the theorem is. Try to explain the theorem. All right, okay. So for the cyclic graph. So the cyclic graph is line graph, is like the line graph, only the last one would connect to the first one. Right? And so you have this. This is a billiard problem. These have been studied by Farber and Tabashnikov, and the formula I'm going to give you was obtained by them, but in a paper in the Annals, or they have 2, Duke and Annals, and they used Totaro spectral sequence and the race shift spectral sequence. Right. So they compute the homology, and then they compute the, and I'm really kind of amazing that they got it exactly right. So, but this is related to the billiard problem because the billiard problem, actually Berthoff's problem, where they were studying, you take a manifold with boundary and more complicated, something bouncing back like this, right? And they look at trajectories like this. So obviously this is different than this, but it could go back to it. So you get the configuration space of cyclic, right? X1, X2, X3 in the boundary, X4. Okay, this is different than this, different than this, different than this. Okay, so they end up rephrasing the billiard problem into a configuration space problem, and it's really beautiful work, right? And they make, so you get this formula here. Okay, this formula is now completely combinatorial. It's a counting problem. When you apply the result I gave you, you get it back immediately if you know this, which is anyway interesting to have independently. No spectral sequence, no shift theory, nothing. And then, of course, you get the stable Arnold-Cohen result, which everybody perhaps knows, the usual configuration spaces of points, of distinct points that, Urs and Hisham use all the time. Because when Km is the complete graph, you get the configuration space. And then when you stabilize it, after one suspension, you get this. The proof of the suspension Am I going too fast? I thought,
I think you're half an hour through.
oh, okay,
Halfway.
all right. So I don't need to rush. But basically, okay, so you get this beautiful form. Right. Yeah, so the number of edges is this A1 is this number of edges. And so in this case, right, the stable splitting is known, but the proof would not apply generally because here the stable splitting here, right? So all the homology classes come from spherical classes, from maps of tori. So in the case of a complete graph, and we conjecture this, or we think it would be true for the general configuration space, graph configuration spaces, that in the usual, the standard classical result for configuration spaces, the classes, as if you take the configuration space with distinct points, then all the homology classes are generated by, say, this rotating around this, you get a sphere, right? And maybe the third point rotating around this, so you get another sphere. All right, so you get the torus, right? So you look at all configurations of points where maybe you fix this, or this is going around this, and this is going around this. Okay, so here you get a map of, if you are in Rn, right, you get a map like this in the configuration space. Here you have 3 points. All right, and all the homology of this guy generated by maps of tori like this. Okay, and so when you suspend, you get everything you want, just because of that property. This is not what we can use, but this is what is used in the. Okay, now the interest here is how do you prove this theorem? Okay, and interestingly, it's the first time I use poset topology like this, and all the methods I'm used to would not apply. And this convinced me of how powerful poset topology is and how beautiful it really is. Really, anyway, I hope I can convince you this is a nice theory, which sort of, I think it's initiated by Whitney and Rota, and then Stanley and Björner basically developed it to a really great extent. So you say, start with a poset with a less or equal order, partial order, which I will not write from now on, perhaps. And associated to, so if you have this poset, 1 is less than 2, 1 is less than 4, this is a hash diagram for it, right? So 2 covers 1 means that 2 is immediately bigger than 1. There's nothing in between, right? So you write the hash diagram of a poset like that. So you order them by immediately one after the other. And then, so you get in fact, like a nerve, right? So you can realize it. Right? So the realization of this here is called the order complex. So the order complex, so to every poset, which you can write like this, you can realize it as a simplicial complex. So you can associate naturally a space to any poset. So actually, I'll take this poset, for example. Okay, 1, 2, 3, 4. So to every, so I start here. These are the vertices. Okay, so I'm going to construct the order complex of it. So this is my P. So 1, 2, 3, 4 would be the vertices. Now, if I have an edge, so I go from bottom to, so I have 1 to 2, 1 to 3, I have edges. And to a path of length 2 like this, I get a 2 simplex. That's it. So to a path of length 2 corresponds to 2 simplex. A path of length 3 corresponds to 3 simplex. And they grew along faces. It's really simplicial complex. Okay, so what's the connection of the graph arrangements the graph configuration spaces with posets, well, through the bond lattice. The bond lattice, as I mentioned, is, I've been talking about it now, right? So if you take a graph, you take these bond elements, the blocks correspond to connected subgraphs, but you can merge them, right? When you merge them and they make another connected subgraph, you get a coarser, a smaller partition covering your original partition. Here's an example. So 1, 2, 3, 4, that's a line graph. So I start with 1, 2, 3, 4, the vertices, 1, 2, 3, 4, 4 vertices, like 4. I can merge 1 and 2, but I cannot merge 1 and 3. Because 1 and 3, if they come into one block, they do not give me a connected graph. So I can merge 1 and 2 and leave 3 and 4 alone. 1, 2, 3, 4. So these are the bond partitions of length 3. These are the bond partitions of length 2. And then I have the bond partition that doesn't show. And so my less or equal is being finer than. I don't know if I'm making sense. It's probably too fast. So, yeah. So this is the bond partition. These elements are the bond partition of this graph. And now I'm putting them in a bond poset. Right. So I say, so if I take 1, 2, 3, 4, so I can merge 1 and 2 because 1, 2 is a connected subgraph, and then 3 and 4 is 2, 3 is a connected graph, 1 and 4 is okay, right? And 3, 4 is good. I cannot put 1, 4. I do not get all partitions.
So is this one thing or two things?
This is a poset. This is a Hasse diagram of the poset.
I see.
This describes a poset, doesn't describe a space. I have to realize it.
But on first sight, I have the same problem. It looks like these are two graphs, but you mean the same because there's no. This is a single poset, right?
Oh yeah.
Just
I'm
visually,
trying to illustrate. I'm trying to tell you about the bond lattice. This is called the bond lattice, by the way. It's a lattice because every two elements have a joint underneath. But this is, yeah, I'm explaining it. So it's like slides. This is a graph on the left-hand side, right? As an example. Now I am putting all the bond elements into a poset. That's all. Right. So now I'm getting a poset. All right. Okay. Perfect. So I have poset. I can use poset topology. How about that? Okay. Now, and I have also a graphic arrangement. So I'm in Rn, by the way. This is traditionally how this thing has been approached. That's why Longueville and Schultz have results on it. Right. So, right. Okay. So to any collection, hopefully anybody knows about intersection lattice of arrangement. Okay. So you have an arrangement. An arrangement is a collection of subspaces. Okay. Now all my subspaces have the same dimension, which makes life a lot easier, nicer actually, incredibly nice. So here, this is a hyperplane arrangement in R2, a line arrangement in R2. So if you have an arrangement of how many? 1 line, 2 lines, 3 lines, 4 lines, 6, 7, 4 lines, right? So you have the 4 lines, right? So you have a division of 4 lines. Then you look at the intersections, and you get a poset by, if you go up, that's inverse inclusion. So if this is less than this, means this is included in this. So you get inverse inclusion, and you get what you call the intersection lattice of your arrangement, right? So if you have an arrangement, you have an intersection lattice. Now, here's the interesting part. When I look at the configuration space of my graph configuration space, it's an arrangement. It's a complement of an arrangement. Because when I say xi not equal to xa, it means I remove the hyperplane. It's not hyperplane. If I'm in Rn, I'm going to remove the hyperspace where xi equal x. It's good dimension n. Okay. So I have an intersection lattice, and the bond lattice is the same as the intersection lattice. Okay, that's the same. Okay, so now what's the whole point? I have my graph to which I have this configuration space, and to this configuration space, I have the lattice, the bond lattice, or the intersection lattice of the arrangement. What's the arrangement? The arrangement is all the subspaces where xi equals xj if ij is an edge. We going back to the whole situation, right? So my configuration space, the graph configuration Rn is the same thing as the complement of this arrangement, because I'm saying I is not xi is not equal to xj if I is an edge. So it's the complement of the subspaces where I equal to. So I realize this as the complement of an arrangement. And how do you compute, and this is a marvelous term by Gorski and McPherson, using stratified Moore theory, but then people have realized that, in fact, it's just Alexander duality. Gorski and McPherson tell you, if you have your poset of intersection, which, as I mentioned, is the same thing as the bond lattice. A lattice is a poset. A lattice is a special kind of a poset. Sorry, sometimes I use lattice, sometimes a poset. Okay, so if you have that bond lattice or intersection lattice, you can get the homology of the whole complement by this one. So Gorski and McPherson tells you that, in fact, here you can put any complement of a subspace arrangement. But okay, I put the one I want, right? And it's the sum over the homology with this Alexander duality shift of the intervals. So for every interval from 0 to x, you get this. So it's too much in one slide. I realize that, but how small can I make it? So suppose you have an arrangement, which is this AIs, okay? And the AIs are like this one, A1, A2, A3 or something, and, right? And then you look at, these are arrangements in Rn, and you want to look at Rn minus the union of this. This is the complement of the arrangement, and you want the cohomology of this. All right, so what you do, you look at the poset of intersection, poset of intersections of this. Okay, so it will be A1. So you start with the what you call the atoms, right? A1, A2, An. This covers 0. 0 could be the, actually it's Rn. And then you take the intersections. A1 intersects A2. If it exists, if it, right? Well, and then the intersection. So you get this lattice, right, of intersections. And if you have an x in this lattice, the interval is everything that is covered by it. You go down all the way, everything beneath it. Right? That's called the interval. So it's a sublattice, or it's a subposet containing all elements smaller than x. This is 0x. So it's a complicated formula. Sorry, it's a very easy formula, but it's complicated to use because you have to care about all the intervals. All right, so you look at all the intervals and you take the homology of those. You realize it. Take the, yes?
Are the these are A1, A2, they're like all codimension 1 in Rn?
No, subspace arrangements. In fact, the codimension n in this case.
Okay.
But they all have the same dimension.
So if you take
Yes,
you take the cohomology of the interval, you regard the interval as its cell complex, right?
exactly.
As its nerve.
Exactly.
So it's not
Right.
just,
This is the order complex or the realization of it.
so maybe one could put vertical bars there or something.
Do you want,
No, I don't know. I mean-
No, I could, yeah, maybe you're right. Maybe because some do, some don't.
That's it.
I totally agree. Yeah, maybe we should, but because you might think of it as just the abstract complex of all these simplices, and then okay.
Yeah, the interval, as you just said, is a poset, right? Itself.
The interval is a poset. Then I take the delta of it.
Okay,
It becomes a
right.
simplicial complex.
Right.
Yeah, it becomes an abstract simplicial complex, but people
Okay, sure. No.
rarely put this also on top
Right.
of it. So I'm sorry if there's too much in the slides. I realize maybe, but there are ideas. I'm just present ideas, right? I mean, the details, you'll find them eventually. Okay. So there is this formula. So I want to apply this formula. Right. Now, the whole idea how to compute anyway, for every subinterval, you want to compute that. Right. Now, the main next idea is that these guys are wedges of spheres. They have to be, right? Why? So, all right. So I will get the homology I want, and I want it to be torsion-free, the homology of spheres and everything. I'll deal with the stable homotopy type. I don't think I'll have time, but at least I'll get to there. All right. So Ziegler and Ivaljevic has this beautiful explanation of Gorski-MacPherson. I don't think it's right. I will go look at it in their books, try to find book theory, but there's many now approaches. Kozlov, who was here, Dmitry, both came here, gave a talk, has a beautiful explanation of this also, papers, generalizations. And the strategy here is to show that every interval is a homotopy type of wedge spheres. And if you know the dimensions of the spheres, you can deduce their numbers. Okay? So if you know a space is a wedge of equal dimensional spheres, to know how many spheres there are, you only need the Euler characteristic. And the Euler characteristic is the A1 of the chromatic. Okay, so shell ability. How do you know that delta is going to be wedge of spheres? This is the main theorem in the theory. This is the main, there's tons of papers about shellable complexes. Shellable complexes are those complex, simplicial complexes. It doesn't have to be percept topology. Are simplicial complexes that have the homotopy type of a wedge of spheres of equal dimension. What's a shellable complex? The shellable complex is, all right, here's the shellable complex. Is you can order the maximal faces of, so it has maximal faces, maximal dimensional faces. You can order them and then reconstruct your complex by adding those in a way that the intersection of each with the previous is along the maximal face. Let me show you. Okay, here, this one, okay? Let me go back. Just, you don't need to read this. I made like some kind of animation. This guy is shallow. It's a union of maximal faces. You can reconstruct it. A shallow is a way to reconstruct it in a nice way. What's a nice way? You start with A, you glue in the next face along a maximal face. Right? You cannot glue it along a vertex. It will not be shallow. Right? Then the next one has to glue along maximal faces to both previous ones. Then the next one has to glue along maximal faces along this, and then this one is okay. So if you can do this, and if you can reconstruct your whole simplicial complex like this, you say it's a shellable complex. And there's a theorem that tells you a shellable complex would be a wedge of spheres. So, for example, this okay, the shelling here is okay. Okay. Did I give an example? I don't know, this is not okay. Can somebody say why this is not okay? It's not shallow. Exercise. Well, it's good. I didn't think of giving an exercise. This is not a shellable complex. Well, right now it's okay, right? I'm reconstructing the simplicial complex. I'm gluing this along the maximal face, then I'm gluing the next. So it is gluing along the maximal face, right? But it's gluing to this along the zero face. It's not the shallow. It should glue to this along the maximal face. Maximal dimensional face. You see what I'm saying? Should I say it again?
Yeah, no, I see it, but like I don't understand why the one previously was okay.
Because this guy is going along this along a maximal.
No, I mean
face.
the preceding example.
In the preceding example.
Like why is
everything is good.
why is this one good?
What is this? Thank you. Because it will have the same problem, right? It's fluent. Oh, I see. So maybe it's what did I do? This is good. This will have the same problem, right? Yeah. My apologies. This is good.
Well, even those
No,
other ones
okay,
on the
maybe.
edges.
I'm sorry?
This one is also on the.
Yes, that's what you mentioned. I would have an issue because it's intersection, the other one, not a maximum fit. Maybe that's not a problem. Okay, thank you, sorry, I did not say. I was made in this last night, so. I don't say.
Yeah, no
Okay.
problem. Like, I was just
Yeah,
wondering.
it's a very good point. So
Yeah.
anyway, that's the whole thing. Let's see, a sharing is a linear order of the facets of a special condition. Pick the first facet, and each new facet added to the list must meet the old complex at the anti-union of maximum proper faces. Maximal proper faces. Yeah. Well, it has to meet at the vertex at some point, but maybe, what was the whole? Maybe this guy. Maybe this guy. Sorry, maybe this is okay. So maybe this is not a counterexample because I don't know. Let's move on. I'll think about it.
Yeah.
Okay. All right. Okay. So here's the main theorem, and then I'll skip many things. Right. If you have a poset, this is the main theorem in the theory. If you have a poset, so let's remove the top bounded poset. Bounded poset means it has a 0 and 1. Exactly my situation when I look at the intersection poset of the lattice, the bond, whatever you want to call it. I start with Rn and put all my thing. At the end, I intersect. It's a central arrangement. So they all intersect. They all intersect at the x. They all contain the diagonal. So all my touch spaces intersect. So I have a maximal element, and I have a minimal element, and what happened here? And if you do, sorry about that. If you look at the order complex of your thing, it's a wedge of spheres. Of how many? It's this many spheres. Oh, right. Okay. Gosh. Okay. So there's one more thing I need to mention, but maybe I could skip to the one application of this. Okay. Okay. Skip for the next 2-3 minutes to an application because right. So the poset is soluble. This is a soluble complex because it's something called geometric. So and so for any, in fact, for any interval of my bond lattice, I get it to be soluble, so I get it to be wedge of spheres. So I can put it in the formula correct to my first. Okay. How many spheres? How many spheres? Is this many spheres? What's this mu? It's not A1. I claim it's A1, but it's mu. Mu, what is mu? Is something with the Mobius function of the thing. So I'm going to skip that. So there's a formula you have to need. Or skipping this. At the end of the day, you get that your mu is up to sine the A1. Okay, and the mu is the just to mention this. If you have a poset, you have a Mobius function. If you have a poset, just take your any poset. Something you learn because you'll see it everywhere. So suppose you have a poset. Or something like this. So suppose you have a 0. So you put a 1 here. Then here you put a -1 because you want this plus this to be 0. Immediately link to it. But here you put -1 because you want this one that's underneath it. You want the sum to be 0. Now what do you put here? Here you put something so that the sum of everything beneath it is 0. So you have to put 1. What do you put here? You want something that the sum of everything beneath it is 0. So you put 0. Right? This is called the Mobius function of the poset. So I had an example, but I won't have time to. If you have this, the poset for the line graph, right? Something like that. So what's the Mobius function for it? You put 1 here. Oh, you start with 1. Right. Then here you have -1 because this immediately linked underneath it is right. So this plus this has to be 0. This plus this has to be 0. This plus this has to be 0. What is this? This and the sum of everything underneath it should be 0. So this plus this, sorry, yeah, this plus this plus this plus this plus this is 0. So this must be 2. So you'll be assigning numbers like this, and out of this you make a polynomial. Sum of these numbers, t to the n minus x. This is called the characteristic polynomial process. And there's a theorem that tells you that it is the same as the chromatic polynomial. Anyway, so I'll skip this, how you get the stable homotopy type. Maybe that was what was most interesting for the crowd, but it did take me a while to explain, so let me skip, I'm sorry. All right, so it's all based on this work of shape. Somehow not so well known because I asked 2 experts, they didn't know about this paper. One did never read it and the other one didn't know about it. And but I was very, very happy to find this. Okay? And he gives a stable splitting for these guys. Non-trivial work in math an hour. Okay, I use this to get my stable splitting. Okay, one application and we're done, Hisham. Okay, one application. How can you use this? For example, and you can use it in many various families of configuration spaces. Just happens to be this one as the simplest. All right, so this is configuration space in the factory or something people call. So suppose you have an R2 and you have obstacles, P1, P2, P3. This can make up spaces.
This color is hard to read.
Right.
Yeah, probably green or blue.
Suppose you're in a factory, right? Let's say take R2, so Rn is 2, and then you have P1, P2, P3, 3 obstacles. All right, and you have points in the factory moving them. I mean, the usual picture people make a factory, and you have a train or something, and you have wagon, and you don't have to collide. And then you look at all the configuration spaces of points. Well, x1 is not equal to P1, x2 not equal to P, and then x1 not equal to x2, x2 not equal to x3, and x1 not equal to x3. Just for the sake of an example, but we have many more examples. So you take configuration space, the usual one, pairwise distinct, but then you say this guy cannot be P1, this guy cannot be P2, or this one cannot be P3. What is the homology of that? What's that space? Just happens to be that, okay, I'm going to tell you what this is. Right? This is called configured space with obstacles. So you have 3 obstacles and you want that your x1 does not hit the first obstacle, x2 not the second one. Take a space and take the box product, take a graph, sorry, I think it's box product with K2. Box product is defined between any 2 graphs, but for K2 is very simple. Take your K3 here, okay, and double. This is your K2, this is your K3, and the box product of K3 with K2 is this kind. Right, so this will be a new graph. Right, then the theorem you can have is that the Poincare polynomial, so as strong as you can have, this space is the Poincare polynomial of the graph configuration space, all notation first shown. So this is the Poincare polynomial of, no, actually, or of the configuration space, yeah, of the graph configuration space corresponding to this, divided by the Poincare polynomial corresponding to K. Right. So that would be a complete description of this graph configuration space with obstacles. And I'm concluding with this one. I thought this was nice because this really goes back to the origin of configuration space, which is called the, I do not have the name for them. Yeah, here. Then the famous Kallel vibration theorem, which is used classically everywhere, which says something like this. You might have seen it for sure. And I'm done with that. So, yeah. If you take the configuration space of endpoints in an array or any manifold, need the boundaries. Okay, just say and then so say configuration points with k points here. So this means that okay, so x1, xk, and you project into any number of smaller numbers of points. So configuration space are r points, but r is less than k. This is a fibration. This is a bump. Okay, that's what people use a lot in work when they look when work configuration spaces and management, for example. And here you have the same thing, but in fact, it's a special case. That theorem is a special case of this generalization which we need in order to build to this theorem, which says that if you restrict, if you have a graph G and you have a smaller subgraph H, maybe you guys have asked this question from the very beginning, right? So I have a map from the configuration space, G configuration space, by forgetting the entries corresponding to the vertices not in H. I get a map to the configuration space of H. Well, that map would be a bundle if H has a special property. It's a relatively complete region, meaning that here's H, here G. If there's a vertex in G that is related, if there's an edge between a vertex in G to two vertices in H, these must be linked by H. They have to be. Otherwise, it will not be a bundle. Thank you so much, and I'm sorry for that.
Thank you, Sadok. Sadok?
So thanks. That was
No,
very
no, I'm
interesting talk.
sorry if I confused you guys. I threw ideas.
This is good.
Maybe more a remark than a question, but so the kind of commodity that is often interesting of configuration space certainly for us would be like if we're in R2, then we'd be interested in the twisted cohomology, or if we're in R3, then we're interested in the cohomology of the loop space, of the configuration space. Do these theorems at all generalize to such situations? So twisted by a local system, I mean, that's the relevant.
But to be honest, I did not look at this at all, but I don't see how to, unless there is an analog of Gorski-McPherson formula with twisted coefficients, then certainly that would be, but then your twisted coefficient has to split in some ways. I don't know. I haven't looked at this, but it's worth it.
Right.
Now, but the loop space on these spaces, are you saying what you want the loop space of these, or
Yeah, the cohomology of the loop space of the configuration space. Yeah. Of course, it's pretty. I mean, up to stabilization, it's not much happening. But I think it's crucial not to stabilize for that.
yeah, no, you cannot stabilize, and there's some sort of causal duality for the standard configuration space. Really nice. So the loop space, the cohomology, the loop space, and the configuration space with the one you know, the complete graph, is generated by these the BIs. So what are the BIs? The adjoints of these spherical classes, right? So the configuration space is generated by these spherical classes, right? And the product of these spherical classes, right?
Yes.
And so you take their adjoints in the loop space, and these generate the cohomology of that modulo, what they call the infinitesimal Young-Baxter relationship. So it's fully understood, but even as
No, right. I know for the complete case, it's fully understood.
Yeah.
But now your generalization does it.
Very good, very good. Yeah, I was asking myself this question. I don't know what the answer is going to be. I don't even know if this is generated by spherical classes, but it seems to be. This seems to be something very nice, analog of the whole. Maybe there's some work more to do, but
It sounds involved, but probably worthwhile, yeah. Right?
yeah, it could be. But we answered what we wanted here, right?
Yes, of course.
So unless somebody will ask us, but we're not. Right? We answered more than what we wanted. I just wanted some structure on these because I wanted to construct some invariants of graphs that I can use for the data.
For neuroscience.
But then it ended up, we say, well, let's just let's have the answer.
The application was
Right.
neuroscience.
Yes,
Yeah.
the beginning was in the,
Okay, other questions? Sadok?
One more, maybe,
Yeah.
if there's time. I was wondering throughout about like applications, where do these graph configuration spaces come from? You mentioned the example of billiards.
billiard problems, yes.
And there I was wondering, isn't in a billiard there's extra constraints on these graphs because the angles will have to match in a billiard, right? So not every graph arises from a trajectory in a billiard. So I was wondering how that actually.
No, these are the cyclic. No, the relation is not with the graph, it's all, they are all cyclic graphs.
Right, but not even all of them, right, will be realized in a given billiard because.
A closed trajectory, so, let's see, so let's say you have a boundary, right? So I think they bounce off a boundary or something. And then, so you start with here and then you go here. Of course, here they have to make a same angle, right?
Exactly,
So
that's what I
angle,
mean.
yeah, right, exactly. That's what governs the whole.
Right.
So you start with x1, you go to x2. x1 is not equal to x2.
So the whole trajectory is actually.
And then this bounces back. It hits x3, but it could hit x1 again. I don't care, right?
Right.
But x2 is not equal to x3.
But the whole trajectory is actually defined by the original angle. Then everything is determined. So I'm not seeing how there's enough freedom. I mean, if you,
Dimension 2, I would say, or any dimension.
well, in a billiard, I mean, by
There's an underlying metric. Maybe that's what you mean.
by Newton's laws, right? Once you if the ball starts in some direction, then the entire trajectory is just
That's
fixed.
right,
There's no
right.
further choice. So I don't see how you have the.
I mean, you have freedom in the shape of the boundary.
Right? Is that the idea that we change the boundary?
Yes.
Oh, I see.
So-
Okay.
So you
That's
change
the
the
point?
boundary.
Okay. So we're asking for all trajectories in all possible shape. Oh, that's what you meant by the metric, maybe.
Exactly.
Yeah.
right, yeah.
That it determines.
So
But
it will
is
be,
it clear that we get a well? Okay, yeah, it will be clear. I see. Okay. All right.
Sounds quite general, yes.
yeah, so I want to introduce Mr. Ahmed Rafiqi, who just joined us from AUS.
Great, nice to meet you.
Yeah.
Very good. Any other questions for Sadok? Okay, let's thank Sadok again for the.
Thank you for your attention and your patience.